Welcome back. Here's a second optional video for Lesson 1 dealing with the MIU problem. You might call this extra credit. And so if you're a more advanced computer science student, if you found this exercise fairly easy, you've already got your data structures, you can report derivations, this is a chance to do a little better, do a little more, and it also should give you a bit more intuition about what theorem proving is about, because some of the same issues that you're going to deal with in this extraordinarily simple system also apply in more advanced inference systems in actual mathematical logics. So let's take a look. The first step in optimization of any software system is going to be measurement, right? You can't make things better if you don't know what better means. So what are a few possible measures of this? First, we could look at big O notation, right? What's the basic characteristic of the algorithm? Is it linear? Is it exponential? Is it some sort of logarithmic scale? Hopefully you can take a look and see how the branching of this system works, what are its characteristics, and make an analysis of what order of computation it is. So you can look at how much time your program takes for each derivation, look at all of the three examples and try to compute how long they take. That should be easy to do. Slightly more involved, keeping a counter would tell you how many steps each example takes. In terms of how many epochs was the way that we referred to it in the previous video. And then not only the epochs, but how many total strings does your program generate. All of these are useful measures. And once you've computed how many strings you're generating in each epoch, then it's also possible for you to calculate the average branching factor. How does the algorithm blow up, right? What's the average increase from one epoch to another? This will also give you an idea for what big O notation this algorithm is. So how many epochs also does it take before you have too many strings to compute in a few seconds? If you give this algorithm the target of MU, you'll get to the point where it just blows up. You can't get to another epoch because it's just taking an inordinate amount of time and a ton of memory. So what is that point? Let's see for your implementation. And once you've thought about how you would do these things by hand, can you then write the code to actually report them, and then run your code with all four examples and see what happens, see what kind of metrics you get reported. Maybe that'll give you an intuition about where there's some opportunities for optimization. Now, there are also optimizations, of course, that one can do with code efficiency itself, right? You could take your Python program and recode it into C, and it's bound to be a lot faster unless you do something very strange. That's one way to optimize, but another way is, regardless of the programming language and its capabilities, can you change the algorithm so the algorithm itself is more efficient? That's going to give you most likely a much greater speed up than just, say, changing languages, although those, of course, can have a significant impact. So once you've measured everything and you've got some statistics that are reported automatically, what can you do about optimization? Well, I've presented the algorithm as a breadth-first search algorithm. We have these epochs, and we expand all the options at every epoch. Is there a way to do, instead of breadth-first search, depth-first search? And if you do depth-first search, what happens? Is that good or bad? So try to think that through and answer that question. And after comparing depth and breadth first, we can look at some more intelligent search, something like A star. So picking the best option at every level and trying to just expand the nodes that are most likely to get you to a solution faster. But the key thing is, what's the cost function, right? So do we prefer shorter strings? Maybe the edit distance of each string to the target would be a good optimization, a good measurement to try to follow in optimizing which node to pick next. And also a crucial thing is, if you implement some of these heuristics, do they still allow for the system eventually to try stuff that's suboptimal? Consider that there might be a way with certain heuristics to get yourself stuck in a local minima where you just go down essentially a depth-first search forever, trying to do very simple things, but maybe you need to have some more complicated option happen in order to get to the solution. You need to jump out of that local minima. That's often a problem with optimization algorithms. So we talk in theorem proving about having heuristics that are fair. Eventually you try everything because sometimes the path to the solution isn't the most optimal local thing that you see. So that's it. Hopefully this gives you some ideas for more advanced students, maybe a bit more of a challenge and a bit more of a preview to the things that one has to consider in a more complicated logical system doing automated theorem proving. All right, thanks for watching. I'll see you in the next one.